Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the definitions and terminologies related to the module of chapter of torsion and springs. Let us begin with what is the torsion. The torsion is nothing but a twisting movement or wrenching of a body by the exertion of the forces tending to turn one end or part about a longitudinal axis while the other end is held fastened or turned in the opposite direction. So what is the meaning here? The twisting moment, if we consider a circular shaft fixed at one end, it is fixed and applying torque, applying the rotary motion by fixing, then it is known as the torsion. So the torsion is here, the two case studies if you see in the figure, in this figure we can see both the ends are applied in opposite direction, then it is known as the torsion. But in the case of the figure A, in this figure A we can see the torsion, one end is fixed and another end is applied the rotary angular wrenching or exertion here, or twisting, we applied the twisting at the other end, so then it is known as the torsion. Here in this case, in the figure B, we can consider the both ends are applied in opposite twisting. Then it is known as the torque exertion of the forces tending to turn one end or the part about a longitudinal axis while the other end is held fastened or turned in the opposite direction. So it is known as the torsion. Then next, if you see the torsional vibrations, here these are the modes of vibration. When the natural frequency, when the excited frequency coincided with the natural frequency of the plate, here we consider the rectangular plate having a 100 millimeter wide and 1 meter length, and here on 10 millimeters thickness of the plate, when it is excited at the natural frequency, the torsional modes, we can observe here how the torsional modes are being taking place. So these are the torsional modes in the form of a deformation at those natural frequencies. The behavior of the plate will be looks like this here. At a different natural frequency, this is at one torsional natural frequency, this is another torsional natural frequency. So these are the natural frequency, the torsional modes can be observed. It is for a rectangular cross section of the plate. Next, if we consider the torsional vibrations of a free bar, it rotates among one end is fixed, another end is free. Then under the frequency of a torsional modal frequency, it will torsion twisting takes place at the other end. Next, what are the assumptions in derivation of the shear stress produced in a circular shaft subject to torsion? What are the assumptions in order to derive the equations of the shear, the pure torsion equation, that is tau by R equal to T by J, that equal to C G theta by L. In this pure torsion equation derivation, the assumptions are made. There are 5 assumptions are made in order to derive the pure torsion equation. That is, the first assumption is that the material of the shaft is uniform throughout. The material of the shaft is uniform. And point number 2, the second assumption is that the twist along the shaft is uniform. And the third assumption is that the shaft is uniform circular section throughout. It is uniform. The shaft is uniform throughout the circular section. Circular section is uniform throughout the shaft. And the material shaft is uniform. There is no, the properties of the material, it's the same material throughout the shaft. Uniform throughout the shaft, that means it is isotropic. The next fourth assumption is that the cross section of the shaft which are plane before twist remains plane after twist. And all radii which are straight before twist remain straight after twist. These are the 5 assumptions are made to derive the shear stress produced in a circular shaft subject to torsion. The derived formula, the pure torsion equation, is the tau by r equal to 2 by t by j equal to g theta by L. What is the shear stress? The tau is standard for the shear stress, and r is the radius of, here r is the radius, and here where t is the torque, it is Newton per meter, j is the polar section modulus or polar moment of inertia, j, where g is for polar, that section, not polar, g is the modulus of rigidity, where theta is the angle of twist, where L and L is the length of the shaft. Now here, a shaft is under torsion with equal and opposite torques are applied, or opposite twists are applied at the two ends of the shaft. That's what we have seen here in these figures. At equal and opposite, in this one end is fixed, the torque is applied at the end, the torsion takes place. Now, the relation of the pure torsion, the pure shear stress, the relation of the maximum shear stress induced in a shaft subject to twisting moment, that is, the equation is that tau by r equal to c theta by L, where tau is the maximum shear stress, where r is the radius of the shaft, as we mentioned, and c is the modulus of rigidity or section modulus, theta is the angle of twist in radians. Here the modulus of rigidity, unit for modulus of rigidity is Newton per square millimeter, and radius of the shaft is in millimeters. The maximum shear stress is in Newton per square millimeter. The angle of twist, the unit for angle of twist is in radians, and the length of the shaft in millimeters. And there is another relation. When a circular shaft is subject to torsion, the shear stress at any point varies linearly. It varies linearly from the axis of the surface, from the axis to the surface. From the axis to the surface. The meaning here it is, if the shaft is here, the circular cross section, and the cross section of the shaft is circular, it varies. How it will vary? It varies uniformly from the center to outside the surface of the shaft. It is the maximum. And that equation is that tau by r equal to q by r, where tau is the maximum shear stress on the surface, where capital R is the maximum radius, and q is the shear stress at a particular section, where q is the shear stress at a particular point, and small at a radius of small r is the capital R. If we consider the circular cross section, is the capital R at the surface, where the shear stress is the tau. And at a ring, circular ring, if we consider it, at a ring, it is the small, at this point it is the small r. What is the shear stress? It is the q, is the shear stress. At this point, what is the shear stress? That is denoted by q, and at the radius r, the tau is the maximum shear stress at the radius of capital R, that is the maximum radius of the surface. So this equation indicates the relationship between the maximum shear stress to at a radius r, shear stress at a radius small r. Now here the next one is the shear stress is maximum. The shear stress is maximum on the surface of the shaft, and it is minimum at the axis of the shaft, or another manner it is zero at the axis of the shaft. So the shear stress is always maximum at the surface, and it is zero at the axis of the shaft. And next, if you want to know what is the torque transmitted by a solid shaft, that is the torque transmitted by a solid shaft, that is a T equal to pi by 16 times a tau d cube. Okay, what is the T here? The formula for this maximum torque transmitted by a solid shaft means where T is the torque, that is the T is for torque, and tau is the shear stress, and where d is the diameter of the shaft, diameter of the solid shaft. The next, if you want to know the torque transmitted by a hollow circular shaft, what is the torque transmitted by a hollow circular shaft? The torque transmitted by a hollow circular shaft, capital T equal to pi by 16 times tau, that is again tau d naught power 4 minus di power 4 by d naught. this d are not a do. This is do power 4 by di do power 4 outer diameter power 4 minus inner diameter power 4 by outer diameter. This do is the outer diameter of the shaft, di is the inner diameter of the shaft, and tau is the shear stress, and T is the torque. Pi by 16 times tau outer diameter power 4 minus inner diameter power 4 by outer diameter. The next one is the relation between the torque, polar moment of inertia, and the shear stress. So what is the relation? This is the between the torque T, polar moment of inertia J, and the shear stress T, and also it is the relation for the modulus of rigidity and length. So the relation here, this is the equation. This equation is known as the pure torsion equation. That is T by J equal to tau by R, that equal to C theta by L. Okay, what is the I here? Where I here they mentioned J. The J is the polar moment of inertia. J for polar moment of inertia. Polar moment of inertia for solid circular shaft, that is pi d power 4 by 32. Polar moment of inertia for hollow shaft, that is pi by 32 times d naught power 4 do power 4 minus di power 4. Outer diameter, di is the inner diameter. This is for hollow shaft and for solid shaft. What is the torque here? This is the T by J, and T by J equal to tau by R equal to C theta by L, where C is for modulus of rigidity. Modulus of rigidity. Now, this is the equation, this pure torsion equation. It is very important equation in order to find out the variation of the shear stress across the section of the beam. Next, the ratio, what is the polar section modulus or torsion section modulus? The torsion section modulus that equal to ratio of the polar moment of inertia to the radius of the shaft, that is the maximum radius. Radius of the shaft is known as the polar modulus, or another name is called torsional sectional modulus. It is denoted by ZP, Z suffix P. ZP equal to J by R. It is for solid shaft. The polar torsional section modulus ZP equal to pi by 16 times d cube, and the polar section modulus for a hollow circular shaft, it is pi by 16 d naught times do times do power 4 minus di power 4. This is for hollow circular shaft. So ZP also represents the strength of the section, as we have studied the section modulus in the variation of the bending stresses or flexural stresses. So here the maximum moment resistance depends upon the section modulus in the case of the variation of the bending stresses. Here in the case of the variation of the shear stresses on the torsion topic, where the torsion section modulus, that is ZP equal to J by R. So this ZP also represents the torque. If the torque is maximum, that is T by J equal to tau by R. T equal to T times R equal to J times tau, and T equal to J by R times tau. This J by R is nothing but polar section modulus, torsion section modulus, that is ZP times tau. So the torque is maximum here. The torque, when torque becomes maximum torque, it can be transmitted when the ZP is the maximum. It is proportional to. So here the section modulus, the torsional section modulus is maximum. That means here the torque is maximum. That's a ZP, that's torsional section modulus for hollow circular shaft. ZP equal to pi by 16 times d naught. That is d naught power do pi by 16 times do outer diameter power 4 minus inner diameter power 4. This for hollow shaft. Next, the next point is that what is the strength of the shaft means. What is the strength of the shaft? The strength of a shaft means the maximum torque or the maximum power the shaft can transmit. If the torque is transmitting the maximum power or maximum torque, that means the strength of a shaft is maximum. As we have discussed in before slide, that is as we have studied in bending stress, the moment of resistance is maximum when the section modulus is maximum. That's why the section modulus represents the strength of a beam. Similarly here, the torsion, if the maximum torque here, that also represents the torsional section modulus. So if the torsional section modulus is maximum, the torque will becomes maximum. When torque becomes maximum, the power transmitted by a shaft becomes maximum. That's why the torque transmitted or maximum power represents the strength of a shaft. What is the strength of a shaft? The significance of a torque is the strength of a shaft. Then here, another important terminology here, it is what is the torsional rigidity. The torsional rigidity is the product of section modulus, modulus of rigidity times polar moment of inertia, that is C times J. That the product of modulus of rigidity and polar moment of inertia of a shaft is known as the torsional rigidity. The torsional rigidity also known as the stiffness of the shaft. Generally, we know the stiffness S equal to load per deflection, that is the stiffness of the beam. But here, that is another, the load per deflection, that is also stiffness of the shaft. But another definition of the stiffness of the shaft is called torsional rigidity. The torsional rigidity is equal to C times J, that Cj equal to TL by theta. Now here, how the TL by theta comes? T by J equal to the pure torsion equation C theta by L. Now make it TL by theta equal to Cj. The Cj equal to TL by theta, that Cj is known as the torsional rigidity, product of the modulus of rigidity and polar moment of inertia. Another definition is the torsional rigidity equal to torque times L by theta. This is also known as the torsional rigidity. Here T for torque, where T stands for torque, L means length of the shaft, and the torsional rigidity becomes a torque when if L equal to 1 meter and theta becomes 1 radian and a theta equal to 1 radian, then torsional rigidity equal to torque, that is a T, that is a Newton meter. The torsional rigidity becomes the torque. Now here, that is the torsional rigidity. We have studied torsional rigidity and also torsion section modulus. The torsional section modulus is ZP, that ZP equal to ratio of the polar moment of inertia to the radius of the shaft. The ratio of the polar moment of inertia to the ratio of the shaft is known as polar modulus or torsional section modulus. It is denoted by ZP. And what is the unit for this? Unit for polar moment of polar section modulus here. The ZP unit is that millimeter cube, cubic millimeter. That is the unit for torsion section modulus or polar modulus. The next, what is the power transmitted by a shaft? The power transmitted by a shaft in terms of the speed and torque, that equal to 2 pi nt by 60. 2 pi n, where n is the speed of the shaft in revolutions per minute and t is the torque. Next, this is what so far we discussed about the torsion related formulae or torsion related definitions. Now coming to one more, that is torsion related, and also torsion, when torque transmits, there is the energy it will be stored. The strain energy stored in a shaft due to torsion, the strain energy that equal to tau square by 4 times modulus of rigidity times volume. This volume is area into length. That is for solid circular shaft. If it is for hollow shaft, that is tau by 4c d square that is capital D square plus small d square times volume. This for a hollow shaft, where d is the external diameter and small d, capital letter D is external diameter of the shaft, small letter d internal diameter, and T is the modulus of rigidity. No, modulus of C is the modulus of rigidity, capital C, modulus of rigidity, and tau is the shear stress on the surface of the shaft. That means maximum shear stress of the shaft. And V is the volume. And here, that's what, these are the known parameters, unknown parameters here. These are the, what is the D, capital D, small d, capital C, tau, and volume V. Now, polar moment of inertia, that is for a solid shaft, that is J equal to pi by 32 times d power 4, and J, the polar moment of inertia for a hollow shaft, that is pi by 32 times capital D power 4 minus small d power 4. We have already studied pi by 32 times d power 4 minus di power 4. Here capital D or DO indicates outer diameter, small d or di indicates inner diameter. Is the polar moment of inertia of a hollow shaft. Next, if you want to further more explanation deeply, what is the power transmitted by a shaft, already covered, that is 2 pi nt by 60. The unit for this is in watts, power. The power, another definition is called omega by times torque. This omega is nothing but 2 pi n by 60, or it is also known as a T omega. This is where omega is here, that is 2 pi n by 60 is the omega. That is the revolutions per minute, that means revolutions per second, that means radians. It comes here, omega equal to 2 pi n by 60, where n for revolutions per minute of the shaft, RPM of the shaft, T is the mean torque transmitted, it is in Newton per Newton meters, omega is the angular speed of the shaft. Now we covered so far the definitions related to the torsion. Now coming to the springs, the second part, definitions. The springs are mainly useful for storing the strain energy. The storing, when the load is applied, that energy is converted into, in the phase of strain energy, it will be stored. It absorbs the energy. So springs are the elastic bodies which absorbs energy due to resilience. There are two important types of springs. Number one, laminated or helical springs. Laminated or leaf springs. Another one is helical springs. Again, the helical springs are categorized into two categories. One is closed coil helical spring, closely coiled helical spring. Another one is open coiled helical spring. Open coiled helical springs. The closed coil helical springs we are going to study here, and the maximum, the stress, what is the shear stress, derived expression, shear stress expression, deflection expression, stiffness expressions we have studied in the previous sessions. Now coming to the leaf spring. In the leaf spring, what is the maximum stress developed in the plates of a leaf spring? This is the derived expression. The stress expression is that 3 times WL by 2N BT square, where W is the point load acting at the center of the leaf spring, and L is the span of the leaf spring or length of the leaf spring, where N is the number of plates, B is the width of each plate, and T is the thickness of each plate. This is the leaf spring consists of, you will see here. This is the laminated leaf spring. The leaf spring consists of, yes, the point load acting at the center, the camber, and the master plate, the gradual plates, and rebound clips. There are two rebound clips. These are the graduated plates or leaves. These are the two ends. These are known as I ends. What is the L? The length of the plates. This is span. So this figure indicates where it is applicable. In the case of four-wheelers, in order to absorb the energy, elastic bodies which want to absorb the energy and gives comfort to the passengers or to the vehicle, not to distortion, not to get damaging the vehicle. Now this is the deflection in this laminated, how when the load is applied, the deflection takes place, it absorbs energy. And if you apply the leaf spring, these are the leaf spring on the roads. It gives the comfort to the travelers, passengers, these leaf springs. And as we mentioned here, there are two types of helical springs. One is closed coil helical springs. Another one is, this is the closed coil helical spring. This is the open coil helical spring. And what is the difference between closed coil helical spring and open coil helical spring? In the case of the open coil helical spring, there is the pitch distance between two coils. Here, what is the distance? The pitch is very low here in comparison to open coils. As in the case of closed coil helical spring, the pitch is low in comparison to open coil. And we can see here, not only that, the helix angles is small in the case of closed coil in comparison to open coil. So this is the physical, this figure indicates the live model, like a live picture of a closed coil helical spring. And it is for open coil helical spring. Now, the expression, the deflection of again, the laminated spring, the deflection, that is sigma, deflection equals sigma times L square by 4 ET, where E for modulus of elasticity, L for length of the spring, and T is the thickness of each plate with a small t, and sigma is the maximum stress developed in the plates. Okay, and as we have studied in helical spring, there are two types of helical springs, closed coil and helical open coil. Okay, but these closed coil and helical coils, as we have studied here, the helix angle is small for the case of closed coil in comparison to open coil. Now, the maximum stress derived for this in the case of a closed coil helical spring, that is 16 times WR by pi d cube, where tau is the shear stress, W is the axial load on the spring, R is the mean radius of the spring coil, and D is the diameter of the spring wire. And next, deflection for the case of closed coil helical spring, the deflection equation, that is the deflection expression, is that 64 times WR cube N by CD power 4, where N is the number of coils, W is the axial load, R is the mean radius of the coil, C is the modulus of rigidity, and D is the diameter of the wire. And what is the strain energy stored in the case of closed coil helical spring? The strain energy stored, U equal to 32 times W square R cube N by CD power 4. Here it is 64 times WR cube N. In the case of here, 32 times W square R cube N by CD power 4. That is the strain energy stored in the closed coil helical spring when the axial load is applied. What is the stiffness? The stiffness equal to load per deflection. That is the load per deflection. That is the load per, what is the deflection? 64 times WR cube by N by CD power 4. So WW get cancelled. That means CD power 4 by 64 times R cube N. The stiffness, CD power 4 by 64 times R cube N, where C is the modulus of rigidity, R is the mean radius of the spring coil, and W is the axial load on the spring, N is the number of coils, and C is the modulus of rigidity. So this is the total stiffness of the spring. Now here, the references for this case, we followed only one textbook, and some of the reference already mentioned, that is the R.K. Bansal followed for this topic. Strength of materials for the edition, new edition, we followed here. So in this session, we covered definitions and terminologies and what is expressions used in the case and the chapters of the spring, torsion and the springs. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.